Hi, and welcome to the very first video presentation of the DronoBox workshop. My name is Lars, and I'll be doing the presentation today. First of all, I want to apologize for the lower microphone quality. I have to record this during Corona time, and thus I have to use the microphone of my headset. The DronoBox is an initiative of A3T, or simply Drone Team, and is made possible by the design lab of the University of Twente. So, let's get started. So, what is A3T exactly? Well, A3T stands for Aerobatic Tech Team Twente. And Aerobatic Tech Team Twente is one of the so-called student teams of the University of Twente. We as a student team try to accelerate drone innovation for humanitarian aid, and we do that by doing the following. First of all, we participate in a competition focused on humanitarian aid. For example, this year we participated in the UAS challenge. In humanitarian aid challenges, you usually perform a simulated aid mission, where you, for example, need to drop an aid package on a given coordinate. Furthermore, we explore and develop ourselves. So one day per week we work on drone projects of our own interest, together with others, or just by ourselves, and figure out what we think is interesting about drones. And of course we apply our knowledge, so we share what we do and what we've learned with others, and we give workshops just like this one. Alright, enough about A3T, let's get back to the workshop. Today I will talk about the theory about drones, which means I will cover the following two things: drone anatomy and control methodologies. So let's get to it. First things first. You've probably heard about a drone before, and I bet you know that it flies. But did you also hear about UAV? And how is a UAV related to a drone? And let's make it even more confusing, because there's also something called RPAV. So, of course, all these terms are related to each other. But what is what exactly, and what does everything mean? So let's have a look at that. Well, the official term for a drone is actually unmanned aerial vehicle, UAV short. And this can either be a remotely piloted aerial vehicle, RPAV, or fully controlled by onboard computers, which makes it an autonomous vehicle. The term drone is much more known among people, and we don't know why this is preferred over UAV actually. Well, what we do know is that drone was originally applied to pilotless airplanes used for target practice, and since then people tend to use the term drone for each unmanned aerial vehicle. Now, with that being taken care of, we can start to look at the drone anatomy. So, what are the parts of a drone exactly? Let's figure that out. Okay, we consider the drone to be consisting of 7 elements, and of course, those are only the basic parts. So, what are these 7 elements exactly? Well, we start with a frame. Then we also have a power distribution board, PDB short. A drone also has multiple electronic speed controllers, EEC short. We have motors, flight controller, propellers, and of course a battery. Let's start with the frame. The frame is basically the skeleton of the drone, because it keeps everything together and all the parts are assembled on it. Let's look at some examples here. Below we see 2 high quality frames, the left one made of carbon fiber and the right one of aluminium. Both are strong and very suitable as a drone frame. However, carbon fiber is lighter, has a sufficiently higher stiffness, and is also more rigid than aluminium. So carbon fiber is way more often used than aluminium. If you have less money to spend, you can also go for a lower quality frame, for example, made of plastic. However, if you have a laser cut to your availability, we recommend you to make one out of wood, just like we do, because wood is easily manufacturable, it's cheap and also very light. Next we have the PDB, which stands for Power Distribution Board, and as the name already implies, it distributes power. Let's look at some examples. The one below in the left corner is a simple one, because it can only distribute the battery voltage to all the EECs, which we'll talk about a bit later. The one above it is a more standard one. This is actually also the one we use for a DronoBox, and besides distributing the battery voltage to the EECs, it's also capable of supplying a constant 5V and 12V output, which could be useful for other components. The one to the right of it is a more complex PDB, and it's actually a PMB, which stands for Power Management Board. This means that besides distributing power, it's also taking care of signal traffic to all the other electronics. Alright, as promised, the EECs. EEC stands for Electronic Speed Controller, and by applying different voltages to the motors, it's capable of controlling its speed, or angular velocity to be more precise. An EEC is chosen for its maximum current it can handle. For example, if you look at the EEC above in the right corner, this one could handle up to 30 amps. and actually that's also suitable for our drone, for our DronoBox drone. The one to the left of it can actually already handle 110 amps, so that's almost 4 times as much as the DronoBox one. And if you really want to use heavy duty motors, you could consider to use the one below it, which can even handle 280 amps, so that's almost 10 times as much as the one of the DronoBox. Alright, let's talk about motors now. The most commonly used type of electromotors among drones is the so-called brushless motor. A brushless motor is basically an electromagnetic core with a permanent magnet around it. When electrical energy is applied to the different coils of the electromagnet, then through a magnetic field this is converted into kinetic energy of the permanent magnet around it. So it's basically a rotating magnetic field that causes the motors to spin. The first thing to consider when choosing a motor for your application is of course the amount of thrust it can provide, or the amount of weight it can lift. But besides that, there are two more important parameters to consider. The first one is how efficient is this motor? So how much power does it drain from the battery in order to provide the amount of thrust it has? And secondly, what's the kV number of the motor? kV stands for RPM, rotations per minute, per voltage applied to it. So it basically is a measure of how fast the motors can spin. There's a direct relation between the kV number and the efficiency of the motor. Namely, the higher the one, the lower the other. So motors with a high kV number are capable of having a high end speed, but are not that efficient, while motors with a lower kV number aren't capable of moving around that fast, but are more efficient, and thus the battery has a longer lifetime and the drone can fly for a longer time. Okay, let's look at some examples to clarify this up a bit. The motor in the right corner above, the BR2212, is a motor capable of producing around 1 kilogram of thrust and has a kV of 1000. This is also the one we use for the DronoBox. The one to the left of it, the Sunny Sky, the black motor, is a motor capable of producing around 20 kg of thrust, but only has a kV of 100, so that is only a tenth of the BR2212. So this means that the BR2212 has a higher end speed, but is less efficient than the Sunny Sky, so it drains more power, and is also capable of producing less thrust than the Sunny Sky. Let's look at one more example. The other black motor in the bottom, this is actually the U15XXL, is capable of producing 100 kilograms of thrust, so this is really a heavy duty motor. It only has a kV of 25, so this means that this motor is more efficient than the Sunny Sky and way more efficient than the BR2212, but it isn't capable of rotating that fast. Next up is the flight controller, and as the name already implies, it's the controller of the drone, the brains. Everything is calculated there, and it uses sensors like gyroscope and accelerometer to determine its position and its desired heading, for example. We consider two types of flight controllers, the ones with autonomous capabilities and the ones without. The ones without are usually applied to racer drones, since racer drones are remotely piloted and thus don't require any autonomous capabilities. The most popular autonomous flight controller is the so-called Pixar. The original one was fabricated by 3DR, that's the one to the right, but it was later on replaced by the one to its left, which is from Emro and called the Pixar 2.4.6. There is also a Pixar 2.4.8. This is actually not an original Pixar, but a replica of the ones I just mentioned before. It's basically the same, and since it's a replica, it's cheaper, so we choose to use this Pixar for our DronoBox. The newest Pixar is the Pixar 4. This is the one with the newest technology and the most reliability. So if you want something good and something to rely on, you should definitely choose the Pixar 4. In order for a flight controller to work, it needs software. That's why each flight controller has its own software stack or flight stack. For autonomous flight controllers like the Pixar, you can either use Autopilot, which is the most popular one at the moment, or Peaks for Autopilot, which is from Pixar itself. For non-autonomous flight controllers, so usually for racers, there are a lot of different ones, and each flight controller specifies the software stack suitable for it. At last, the propellers. Where would we be without those? Propellers come in different materials. Think about wood, plastic, carbon fiber, and in the case of the oranges one shown below, in nylon. These nylon propellers are also used for the DronoBox, and they come in different colors. When you go to the testing data of your motor, you will find a prop specified there. So in the case of the BR2212, you'll see we need a prop with the code 1047. So what does this 1047 mean? Let me explain to you. The 10 stands actually for 10 inch, and that's the diameter of the propeller. While the 47 stands for 4.7 inch, and that's the pitch of the propeller. And what's the pitch exactly? Well, the pitch is basically the distance a propeller would travel after one full rotation, and that's it. If you want to go for a 3-blade propeller, which is handy because they are smaller, you could do that, but you need to keep in mind that if you have a 3-blade propeller that has the same thrust as a similar 2-blade propeller, that would be less efficient, and thus your battery runs out of energy faster. Alright, last but not least, the battery. I've mentioned the battery multiple times before, and I think you guys all know what it does. It supplies power to all the electronics. Let's have a look at the picture above in the right corner. The first thing to consider is the voltage of the battery. Each battery has a number of cells, and this number of cells is represented by the so-called S number. In this case, it's a 4S battery, so that means that the battery has 4 cells. A cell represents 3.7 volt in average, so that means that this battery has a total average voltage of 14.8 volt. Of course, a fully charged battery has a higher voltage, and a fully discharged battery has a lower voltage than the average voltage. The next thing to consider is the capacity of the battery. The capacity basically represents the amount of energy stored in the battery. So the higher the capacity, the more energy the battery can store, and the longer the flight time of your drone can be. There's also a C rating mentioned on the battery. If you multiply the C rating with the capacity, you obtain the maximum continuous current the battery can supply without getting internally damaged. Sometimes a second C rating is mentioned. If you multiply this C rating with the capacity, you obtain a peak current the battery can supply. And a peak current can be supplied for around 10 seconds before the battery gets internally damaged. Usually a battery has 2 cables, the main lead and a balance lead. The main lead is the power plug of the battery, so this one goes in the PDB. While the balance lead is capable of measuring the independent cell voltages. So if you plug this balance lead in the so-called battery alarm, that's the black box below this picture, you'll be able to display all the different cell voltages and the total voltage. Furthermore, you can set an alarm. And this alarm will beep when the battery voltage drops below a certain amount. And then you will know that you have to charge your battery, for example. So, now we know all the 7 elements of a drone. So let's get to the next point, control methodologies. So how exactly do you control a drone? We'll start with the flight basics of a drone. So, when we're going up or down, we call that heave. Left and right is called sway, forward and backward is called surge. When we're tilting in the forward or backward direction, we're calling that pitch, while tilting to the left or right is called roll. And finally, when you're turning left and right, you call that yaw. In order to surge, you first need to perform pitch. So actually when we're flying forward and backward, we're both pitching and performing surge at the same time. And that's why we chose to only call it pitch and leave surge out. The same thing applies to roll and sway. Now, let's have a look at the propeller configuration of a drone, or a quadcopter to be more precise. In a quadcopter, 2 propellers need to spin in the opposite direction of the other 2. In this way, you will cancel out torque and prevent the drone from spinning around its own axis. If you do want to create a torque in the drone, you just make sure that you increase the speed of the motors that spin in the same direction, and you'll be able to perform yaw. Now, in order to perform pitch and roll without creating any torque, you need to make sure that the motors that are diagonal spin in the same direction. I'll illustrate why this is. So, for example, we're pitching in the forward direction. Motors 2 and 4 spin faster than motors 1 and 3. And in order to cancel out torque, we need to make sure that the motors that spin with the same rate cancel each other out. So in this case, 2 and 4 need to cancel each other out, and 1 and 3. And this is also the case. Let's look at roll. So, for example, we're rolling to the left. 1 and 4 are spinning faster than 2 and 3 then. And again, in order to cancel out torque, the motors that spin with the same rate need to cancel each other out. So in this case, that's 1 and 4 and 2 and 3. So you can see that this is the only way to make sure that the drone flies and can perform roll, pitch and yaw independently from each other and without creating any torque unnecessary. The next thing I want to discuss, and actually also the last, is the remote controller. The remote controller makes it possible for a pilot to control his or her drone remotely, and I've shown 2 examples here. The one at the bottom is the FlySky Taranis X9D Plus, and this is one of the most popular controllers on the market right now. It's used a lot by professional racers, but it's quite expensive though. The one above it is the FlySky FSI6, and this one is way more cheaper than the FlySky, but it still has a fine quality for its price, so that's why we use it for the DronoBox. In order for a remote controller to communicate with the flight controller, we need a receiver. Not every receiver is compatible with every flight controller, so make sure to check this in the specifications. A popular receiver for the FlySky Taranis X90 Plus is the FlySky X6R and is capable of communicating with our type of Pixar through S-Bus. While for the FlySky FSI6 a popular receiver is the FlySky X6B. And this one is capable of communicating with our type of Pixar through PPM-SUM. So the last thing we have to check is how a remote controller is configured. There are multiple so-called modes available, but the most popular one is mode 2, or the most common used one. And it's configured as follows. The left gimbal controls throttle, so heave by going forward and backward, and yaw by going left or right. And while the right gimbal controls pitch by going forward and backward, and roll by going left or right. And that's it. I hope you guys liked this video, and if you don't want to miss the next one, make sure to subscribe to this channel. Also check out our social media channels on LinkedIn, Facebook and Instagram to check out all the other cool drone stuff we're doing. Thank you for watching, and we'll see you guys the next time.